Okay, in this video I'd like to introduce what we call the ideal gas law. The ideal gas law is also derived from the individual gas laws that we've discussed in earlier videos. So I just want to remind you that when we take the individual gas laws that relate the individual properties of a gas, the volume, temperature, and pressure, we get this relationship. We get pressure times volume divided by temperature equals some constant K. And you may recall that when I added the Avogadro law, we ended up adding the number of moles of the gas into this relationship. And that constant K became a new constant, which we called R, the gas constant. So this is a variation of the combined gas law that adds in the number of moles of gas by considering Avogadro's law as well. So this relationship, PV over NT equals R, is a new proportionality. It's a new proportionality relationship between the pressure and volume and the number of moles of gas and the temperature, in Kelvin of course, and that equals some constant R. Well, we can rearrange this equation by bringing N and T over to this side of the equation. We multiply both sides of the equation by N and T, and so it's canceled out over here. And so we get PV equals and then RNT. And this equation is much more commonly seen with the N in front of the R, and so we get PV equals N RT. And this is the ideal gas law. This is a gas law that relates all of these properties of a gas along with the gas constant R. You may recall that we have the gas constant R listed on the back of our periodic tables. And there it is, R equals 0.08206 liter atmospheres per mole kelvins. And that's the number that we're going to use for R, as long as our units are in liters for volume, atmospheres for pressure, moles for the number of moles of gas, and kelvins for the temperature. You'll see this number for R coming up later, probably in your second semester of general chemistry, when it's relevant to talk about joules per moles kelvins. But for now, for our ideal gas law, the value for R that we're going to use is this one, 0.08206 liter atmospheres per mole Kelvin. So, here we are. The ideal gas law, where P is pressure in atmospheres, V is volume in liters, N is the number of moles of gas, R is the gas constant, which is 0.08206 liter atmospheres per mole kelvins, and T is temperature in kelvins. I'd like to take a moment just to talk again about the units of R. Notice that we have a little dash here between liters and atmospheres. That doesn't mean that we're subtracting atmospheres from liters. That just means that liters and atmospheres are together in the numerator. So if we were to write this out, R equals 0.08206 liter atmosphere over mole kelvins, okay? And again, this is a derived unit. Don't worry about having to do a lot of math here in this unit. Just because it says liters times atmospheres doesn't mean that you're going to have to multiply all these out and divide all these out. This is just the unit of measurement that R has to be in order to be able to use this number. And it tells us that the volume has to be in liters, the pressure has to be in atmospheres, the N has to be the number of moles of gas, and the temperature must be in kelvins. Now, when do we use this gas law? This gas law, as the name implies, is used when we assume a gas is behaving in what's called ideal behavior. They don't always behave ideally. The gas molecules may stick to each other, the gas molecules may repel each other, and so forth. But we are going to assume that they don't do that, that they behave in ideal gas manner. And that is, you may recall, one of our early postulates of the kinetic molecular theory of gases that says that gas particles do not interact with each other except to collide and bounce off of each other. So that's what we mean by ideal gas behavior. It's a very good close approximation that will allow us to calculate properties of a gas by making this assumption that they don't interact with each other except for when they collide and bounce off. So let's deal with our first sample problem. We have sample problem A. What is the volume? So we're looking for V of a 1.00 moles. There we have our N value. What is the volume of 1.00 moles of an ideal gas? So we're going to be able to use our ideal gas law at STP. You remember what STP is? It's standard temperature and pressure. So what is standard temperature? It's 0 degrees Celsius, and that's considered to be an exact number, so it's not going to limit us in our calculation. Standard pressure is considered to be 1 atmosphere of pressure, and that's also considered to be exact. So that will not limit us in our calculation. So we have our ideal gas law, PV equals nRT. I'm asked to solve for volume, so I need to get volume by itself on one side of the equation. So I need to get rid of pressure here. The way I get rid of pressure is I divide that by pressure, and if I do it to one side of the equation, I have to do it to the other. So I have my new rearranged equation, volume equals nRT over P. So I'm just going to start plugging in values. nRT over P. So what is my N value? It's 1.00 moles of the gas. R, well, I'm going to use my gas constant R, 0.08206 liter atmospheres over moles kelvins. What is my temperature? I'm told that it's 0 degrees Celsius exactly because it's standard temperature and pressure. And so I know that I need to add 273.15 to that. So 0 plus 273.15. And this is going to give me my temperature in kelvins. And so since I know that that 0 is exact, I can keep all of these digits. 273.15 kelvins is my temperature. So there we go. My T temperature, 273.15 kelvins. All over pressure. Standard pressure is 1 atmosphere. Again, this is assumed to be exact. So this is an exact number. It's not going to limit me. So my sig figs are going to be limited by those 3 sig figs right there. So I'm going to do the math in my calculator, and then I will have my answer, and I'll round it to 3 sig figs. And my calculator gives me a number, which if I round it to 3 sig figs, gives me 22.4. What are the units here? Well, I was solving for volume, and I can see the moles cancel with the moles, the kelvins cancel with the kelvins, the atmospheres cancel with the atmospheres, and it leaves me the liters, right, which is what I should get for a volume. 22.4 liters. So what is the volume of 1 mole of ideal gas, 1.00 moles of an ideal gas at STP? 22.4 liters. That's about the size of a beach ball filled with gas. So larger than a basketball, about the size of a beach ball. I'd like to take a quick moment to talk about this number. This number may be a number that you have vague memories of, 22.4 liters per mole. And back in your fundamental chemistry, this was probably even used as a conversion factor to convert between liters and moles of a gas at STP. In this class, we are not going to do that. We're not going to use this number as a conversion factor because we are virtually never going to have a gas at exactly STP. It's highly impractical to consider STP for working with gases. We virtually never deal with gases at these conditions, at 0 degrees Celsius exactly, and 1 atmosphere of pressure exactly. So although it's nice to know that every mole of every gas, regardless of its identity, will occupy 22.4 liters of volume at exactly standard temperature and pressure, it's not going to happen for us. And so I am not going to be giving you any more problems that use this number as a conversion factor, or indeed that ask you to calculate anything at STP. Yes, in your fundamental chemistry course, you may have done that to introduce you to the concept, but we're not going to do it anymore. Instead, you will have to use the ideal gas law to calculate what the properties should be, the volume or the pressure should be, based on the actual temperature and actual pressure that is given to you in the problem. Now, having said that, I'm concerned that by drawing attention to this number, that I will plant a seed and some of you may end up using it as a conversion factor. But please don't. We are not going to use this as a conversion factor. Not a conversion factor. For most of our work. Okay? All right, so not a conversion factor. Technically, yes, you can use it as a conversion factor if you're working at STP, but we're just not going to be doing that. Okay, well, moving on, I have another sample problem for you here, and I would like for you to give that one a shot. So if you would please pause the video and work on that one, and when you're done, you come back and I'll work through it with you. Okay, coming back from pausing the video, we're taking a look at sample problem B. And let's take a look at the question, first of all, and make sure that we understand why it allows us to use the ideal gas law and not one of the other gas laws that we've talked about already. So it says, what is the temperature, looking for temperature, of 2.50 moles of an ideal gas occupying 12.5 liters at that pressure? So the first thing I'd like for you to notice is we are not running a chemical reaction here. There is no chemical reaction being discussed. So this is not going to be some stoichiometry setup where we end up doing all of that. The second thing I'd like for you to notice is we are not changing any of these properties. We're not heating it up, we're not changing the pressure, we're not changing the volume of the gas, and therefore we're not going to use the ideal gas law where we have P1V1 over N1T1 equals P2V2 over N2T2. This is not a changing conditions problem. Instead, this problem just says you have an ideal gas, it occupies a certain volume at a certain pressure, there are a certain number of moles of it, what is its temperature? So we're talking about a gas at one set of conditions, not a changing set of conditions. So when we're talking about a gas at a single set of conditions that are not changing, and we are not running a chemical reaction, then we can use our ideal gas law. So PV equals nRT. Let's identify what is given to us in the problem and what we are going to be looking for. What is the temperature? There's our temperature, T. We know that has to be in kelvins, right? Because it's a gas. Of 2.50 moles, that's our number of moles. That's going to be substituted in for N. Of an ideal gas occupying 12.5 liters, occupying 12.5 liters is its volume at 8.65 atmospheres, and there's the pressure, okay? And we're solving for temperature. So if we're solving for temperature, we need to get temperature alone by itself on one side of the equation. To do that, I divide this side by nR so it can go away. Temperature is alone by itself. If I do it to this side of the equation, I must do it over here as well. So my new equation is PV over nR equals T. So I can rewrite that over here. T equals PV over nR. So there's the rearranged equation. I've used some algebra to rearrange it. And I'm going to use this equation, plug in the values that I've been given, and then solve for temperature. The one that I'm looking for now is I want to make sure that the values I'm plugging in to this equation have the correct units. Remember that now pressure must be in atmospheres because R is liters atmospheres per mole Kelvin. So now it does matter what unit of measurement my pressure is in. It must be in atmospheres. And if it's not, I need to convert it into atmospheres so that I can plug it into this equation. Pressure must be in atmospheres, volume must be in liters, N must be in number of moles of gas. So for example, if I'm given grams of gas in the problem, I would have to do a gram to mole conversion so that I could plug it in here. And then I know what the value of R is. It's my gas constant. So it looks like I'm really fortunate in that everything in the problem is already given to me in the correct units. So I don't have to do any side math to convert, and I can just plug in values. PV, so P is 8.65 atmospheres. V is 12.5 liters. All over nR. N is the number of moles, 2.50 moles of the gas. And R is the gas constant, and we know the number that we have to use for that is 0.08206 liter atmospheres, moles, kelvins is the units for the R. And there everything's in its correct units already, so I can just solve for this, and I will get temperature. And you'll notice that the atmospheres will cancel, liters will cancel, moles will cancel, and I'll be left with Kelvin in the denominator of a denominator, which puts it in the numerator, right? If you divide by a fraction, it's the same as multiplying by its inverse, so that would put our kelvins back in the numerator. So let me do the math here now on my calculator. Okay, my calculator gives me a number with a lot of digits, so I need 1, 2, 3, 3, 3. Looks like I need 3 sig figs, so it's going to be 527 kelvins. Okay, there's my temperature of the gas given all of these other conditions. Okay, so 527 kelvins. That's my temperature. It's not a new temperature, an old temperature, it's just the temperature. Because remember, this is not a changing set of conditions. It's an ideal gas at a single set of conditions. And as a result, that told us we could use our ideal gas law. And there we go. I'd like to point out a couple of things about this. First of all, Notice that in the problems that I've done up here, I never mentioned the name of the gas that we were talking about. I never gave you a formula for the gases that we were working with. That's because the ideal gas law is true regardless of the gas. So it could be oxygen gas or nitrogen gas or carbon dioxide or argon or helium or hydrogen gas. As long as we are making the assumption that it is behaving as if it were an ideal gas, the ideal gas law is a valid equation. So that's what this statement is getting at right here. Notice that the volume of, it should have a little of there, of, notice that the volume of a gas does not depend upon the identity of the gas. So yes, at a given temperature, whatever the temperature is, every gas occupies the same volume of space. 1 mole is going to occupy 22.4 liters of space if it were at STP, for example. Therefore, if the temperature is the same, the density of the gas, remember that density equals the mass per volume space. If the temperature of the two gases is held the same, then their volumes are the same. And as we can see in the density equation, if the volume of one gas equals the volume of another gas, then the only thing that their densities are dependent upon is the mass of each gas. So what is the mass of the gas determined by? Well, it's determined by the number of moles. So as we change the molar mass, the mass per mole of a gas, then its density is going to change. So if the temperature is held the same for two different gases, then the density of those gases is only related to their molar masses. So the more massive a mole of gas is, the larger this number will be, and the more dense. So another way of saying that is that as molar mass increases, then we also increase the density of the gas. All right, so I've given you a little sample problem. I think this will be easy for you to solve. Go ahead and pause the video and answer that question. And when you're done, start up again and I'll answer it. Okay, sample problem C says which is more dense at a given temperature. We're assuming the temperatures for the gases are going to be the same. We want to know which is more dense. So you've got oxygen gas. Remember, oxygen gas is O2 because the gas is a diatomic molecule. Or nitrogen gas, N2. So which is more dense? Remember that the density is related to their molar masses. So the higher the molar mass, the more dense it is. So when we're being asked which is more dense, we're being asked which has the higher molar mass. So the molar mass of oxygen is 2 times the oxygen's atomic mass of 16, so it's about 32 grams per mole. And nitrogen, N2, is 2 times the nitrogen atomic mass, which is about 14. So this is about 28 grams per mole. And I could be more precise here and add up the numbers for the molar masses off of the periodic table, but this is sufficient to be able to answer the question. Obviously, O2, oxygen gas, has a higher molar mass than N2, nitrogen gas. So, since it has more mass per mole, then at a given temperature, it is going to be more dense. So, the oxygen gas is more dense.